Our next speaker this afternoon is my colleague Aleksandar Jelenak. And so while we've been looking so far at what can you do from a library perspective to get better performance and to make certain things work, Aleksandar actually looked carefully at what can you do at the file level as a blob, as just a sequence of bytes. And he had some interesting findings, and he will tell us more about that.
All right, so someone tell me the time. Just jump in and tell me it's time to wrap up or something. But otherwise, I'll try to be fast. Because some of the things that basically I might be talking about, my colleague John already covered or at least mentioned or introduced, so it'll be easier than that. So yeah, so I'll be talking about cloud-optimized HDF5 files. And so the term cloud-optimized some file format has been around for 4 or 5 years now, at least in the communities that I collaborate with and work with. And so this is basically an explanation how HDF5 files can be brought into this kind of cloud-optimized state. And obviously there are entities, there are government agencies, there are many places that obviously amassed a huge amount of HDF5 files over time, and they're still being produced even this hour, I'm pretty sure. So the question is, if any of these files do end up in cloud object stores, what does it mean, and how to do, and what can be done to make them much more usable? So what I mean by cloud-optimized HDF5 file, I mean it's still a valid HDF5 file, only that internal structures are rearranged in a way that reduces the number of cloud object store requests for the data or any kind of information in that file. I think it's obvious now that the main mechanism to getting data from cloud object store is using HTTP protocol. And that protocol has a significant temporal latency that kind of throws away the data access advancement a couple of decades back when it comes to other methods like file systems. Again, for differentiation, if I say cloud native format, or if someone else uses that term, what I assume it means is a data format that's specifically developed to take the advantage of distributed nature of cloud computing and key value interface. For example, this is the HSDS schema that my colleague John may not have mentioned, but it's behind the HSDS server. And so just to be clear about that. And obviously cloud native counts as cloud optimized because it's a next level, if you will. I'm going to skip around this just to mention that the main mechanism for reading data from files in object stores is using HTTP range GET requests. So these are typical HTTP GET requests for those who are familiar with HTTP protocol. But this time, essentially, you're not requesting the entire resource. You're basically saying, I want just a part of that resource from this byte and for this many bytes. And so that's basically the main mechanism to reading data from single object. Now, I'll skip this, but to keep on with time, I only want to say that for certain agencies, especially who are now charged to provide their data in cloud, at commercial cloud providers, there is obviously concern how much they need to reformat the data from their archives to these object stores. And also, despite all this popularity of cloud computing or early adopters saying the benefits of cloud computing, for example, in terms of NASA science, downloading HDF5 files, to be specific, is still the most popular way of getting NASA science data. So the cloud optimized HDF5 file, the way I'm thinking about it, is really should live in this golden middle between still being good in cloud object stores, but still being useful and usable by people who would download that file and use it traditionally on their computer. So what makes a cloud optimized HDF5 file? There are two things and one note. First thing, and by far the most important optimization method, is increasing the sizes of data set chunks. So what that size is, it's questionable, depends on some applications, but generally we're talking about several megabytes per chunks. The second optimization thing is to consolidate internal file metadata. And these two things are independent of each other. You can do one, but don't have to do another one, although both done really makes the file super, super cloud optimized. And the note is avoiding use of variable length data types, and I'll explain why. So large data set chunk sizes, obviously, when I say chunk size, I think of bytes. The other thing that maybe people say chunk size is chunk shape. So be careful, these are two different things. And how much is in good? Again, depends. There are some talks that, for example, for AWS, there's a white paper that says if you're doing a rage get request, make it between 8 and 16 megabytes, for example. So that's maybe some number to start with. But it really, I think anything above 1 megabyte is good. Anything really above 8 megabytes would probably too much, I think. And obviously, no matter how large data set chunk is, if it's compressed, you have to take into account that there'll be some time to decompress large chunks. So that also has to go into consideration. One reason why I still live, I guess, with this small chunk sizes, and by small, again, I'm saying from the cloud optimized perspective, is because not a lot of people actually know about data set chunk cache. And there was some talk previously that mentioned these configurations and property creation lists, and how there are so many knobs that you can configure HDF5 library with. I think this is one of the consequences of that. So by default, the HDF5 library comes with the 1 megabyte, which was probably large in 1997. And so, and has not changed since. And so a lot of best practices and things are really, even if they don't mention, they assume 1 megabyte as chunk cache size, and therefore the chunk sizes are coming up really tiny. And so that's one big reason. And I'm trying to inform people that there is data set chunk cache and it can be configurable, and that definitely they should not be producing such small chunk sizes if ever they expect their HDF5 files to end up in a cloud object store. How to set chunk cache size? Obviously, there's the library. It's possible to do it in H5Py already, so that's a good thing. Variable length data types. I mentioned it's a note, but because of the way variable length data is stored in HDF5 files, that storage is not really friendly to the idea that there is a contiguous block of bytes that you can request in an HTTP range request and do something with it. And so the solution right now is try to minimize it as much as possible, or completely avoid it if, obviously would be great. The current methods that basically sidestep HDF5 library when accessing HDF5 data in cloud object stores, they duplicate variable length data outside of HDF5 file. They store it in some other, usually the term is sidecar file. And so they store it there, and so they never actually go for variable length data in HDF5 files afterwards. Obviously, that's the case, then the problem solved. But if there is a lot of variable length data, that sidecar car can really become big and defeats the purpose. So minimize using variable length data in HDF5 data. Variable length data in HDF5 attributes is not such a problem because you get this data differently. And as far as the next optimization method, how am I doing? I'm okay? Fine way. Is consolidated internal file metadata. This is again, one of the big benefits in cloud object optimized access is that there is only minimal amount of data reads, preferably just one, to learn what's in the file and where it is. And this is especially important for applications that are operating with data on a higher level than just HDF5 storage object. And so they need to know the full content of the file in order to generate this understanding of the file, of the data in the file. And by default, the library spreads this internal file metadata in very small pieces throughout the file. And so the number one reason why HDF5 files just copied into object stores and then accessed have poor performance is because of this reason, because the internal file metadata is spread around in very small pieces. So the next slide are about how to consolidate the metadata. Remember, this is an independent optimization feature unrelated to larger dataset chunks. But it can help a lot, obviously. And I ordered this list based on how much data will later be accessed with the HDF5 library. I am, again, as I mentioned, working with communities and users who have developed methods not using HDF5 library. And so the number 2 and number 3 are really very relevant to them. This being an HDF5 user group meeting, it's probably the largest gathering of people who are using HDF5 library. So I think number 1 is really the only option available. So what does it mean, paged aggregation? So there is this thing called file space strategy. And one of these file space strategies is called paged aggregation. It's not default. And unfortunately, it can only be set at file creation, which means that millions of HDF5 files exist now that do not have this file space strategy. Long story short, it forces the library to write data in pages, and it actually separates the internal metadata in separate pages and the raw data in separate pages. So keeps things very clean. But it writes them out in pages that are application configurable. And so if person knows in advance roughly how much its internal file metadata will be, application can set that page size to be big enough to hold all internal file metadata in the single page, and therefore achieving one of the holy grails of cloud optimized access, and that is that there is one request to get all the information about what's in the file. The other added benefit, if you want to access HDF5 files with the HDF5 library, is that there is page buffer cache. And it's only available to this page aggregated file. What page buffer cache does is that it caches these pages that I just mentioned. All right, 4 minutes. And so, so that's that. I'll speed up now. We don't need to talk about this. This is the command line that you can use if you already have HDF5 file and you want to apply page aggregation to it. The next method is file metadata block size. This again has to be set at the file creation, but in this case, all it does, it basically reserves a block in the file for internal metadata. There are no more these pages that are forcing the library to read and write in certain size. So all the other behaviors of the library is the same as in the file system. So it's definitely not a plus for those who want to use HDF5 library. But eventually you still get all the internal file metadata in the single block. And I do recommend that you get the metadata block right so that you are sure that all the internal metadata gets into a single metadata block. Makes things more complicated if it's not. And just to mention, page buffer cache is not available here. So no savings there. The last one is really, oh yeah, sorry, this slide is a useful one. So how to find your internal file metadata. Well, you use H5 stat, and one of these things is called file metadata, and it's going to show you how many bytes are there. So you can decide how much your page size is going to be, or how much your metadata block size is going to be. So the last one of the three methods is kind of the one that's almost completely bypasses the HDF5 library. In this case, you're literally treating HDF5 file as a container of chunks, and all the other information about content is in this specific formatted content stored in user block. In this case, people maybe don't know, but there's a user block. I'm not going to explain that because I'm out of time. But basically, you would scan the content of the file, convert it in whatever representation is appropriate, and then store that representation as a user block. The benefit is that you still get a single file, so it is still a single object in object store, so it makes management of all these files in object stores easier. But and the information about the file is again from the start of the HDF5 file, so there is again one request to get this information. But at this point, you don't depend on the HDF5 library to scan the file and give information what's in the file, because it's already done. And that's pretty much, yes, all I have. And then maybe questions for the last minute or so.
All right. Thanks, Alexander. Do you have a figure just showing a few results, the impact of some of these changes?
Yes, I do. Let me see, chat, there was something in chat, wasn't it? Okay. I was worried about time. Yes, okay. So I do have my chat here. So I use the ISA2 files, like what Matt before me and John talked about. And so so here's the example. So this is a typical file that comes out of NASA, Earth Science Data Processing System. And so if you do the stats on chunks, you see that 500 out of 657 chunked data sets in this file. 582 are between 10 and 100 kilobytes per chunk. There are 36 less than 10 kilobytes, and there are 21 with just below 1 kilobyte. That's death as far as CloudOptimized data X. And so that file should definitely be, rechunked or produced with bigger chunks, obviously. So what I did with this file, I created two versions with page aggregated files. One was with 4 MB, one was 8. I did this deliberately. So there are two pages with internal metadata in the case of 4 MB, and there is only one internal metadata page in case of 8 MB. So that was good to test. Anyway, this slide, when I put the original file in an EC2 instance with a file system, the natural environment of HDF5 library, and my processing task was list me the entire content of the file, all the chunk file locations, all of that information. It took just under a second for that original file. If I put that file into an object store and did the same thing with ROS3 VFD, but any other method as well would work the same outside of HDF, it's 155 seconds. So you work out how that comes out. I would say it's about 150 times slower. And so that, if I use page aggregated files, and I set up my page buffer to be just enough to hold all internal metadata about that file, then the time goes down to 1.3, 1.1 seconds, which is essentially very close to 0.98 seconds of the original file. The interesting fact, though, when you use this metadata block version of the file, with 8 MB. It's not the same. And I was surprised with that. But then when we introduced logging in ROS3 VFD, then I realized why, and here is why. Although you do have internal metadata in one metadata block, the library still makes thousands of requests for that data inside of this metadata block. So in this particular case, there is 6,600 requests. And you can see how many bytes are requested essentially for 0.32% of the file. And this is the graph in terms of time where these requests go into a file. But then I realized, so that's why I kind of put this metadata block as a second option, because still the library doesn't benefit from this metadata block because it doesn't cache it anywhere. So if you have an application that essentially maintains the cache independently of the library and can satisfy these requests for the library, then you can still use metadata block. But that's not current capability of HDF5 library.
Mm-hmm. Great, thanks. I'm afraid we are out of time, so no time for questions, but a reminder, Aleksandar is also a regular presenter at the HDF clinic, so just pick the right Tuesday and ask him anything about cloud optimized HDF5. Thank you.
No problem.